called?
You could just write C 2 by 2.
Alright, fine. So C 2 by 2, the copy of H1 and C 2 by 2, right? So let's say L tilde is C 2 by 2, copy of the Quaternions, a copy of the Quaternions again, and I do think you're right. We can write L tilde basically as, you know, if I call this thing, well, I'll tilde happy here. Let's call this P tilde, right? This is P. So putting a tilde means we
Made it a matrix.
make it a 2 by 2 complex matrix. So L tilde, P tilde should in fact be equal to like R tilde of P tilde, I think. For some appropriate like this kind of 2 by 2 complex matrix.
So we should be able to matrix multiply 2 of those and get back 1. Is that what we're saying?
Right, right. So then you would want L tilde of P tilde time, well, because the, what's the dot product in this formalism?
Ooh. Is it the same one we just used for SU?
Yeah, I mean, I guess you could be like, well, forget about the dot product. Just say you want the length of L. I mean, this I know how to do without scratching my head too much. The length of L of P tilde is supposed to be equal to the length of P tilde, right? But we know that that's the determinant of L, right?
Mm-hmm.
And so the determinant of these 2 by 2 matrices takes over the role of, well, squared length, I should say. Right, and then so that is determinant of R tilde, the determinant of P tilde equals determinant of P tilde, but that holds for all P tilde. So consequently, we must have this is equal to 1.
That's what it was.
Which is to say that
A squared plus B squared.
B squared C squared plus D squared is equal to 1.
Which is SU2.
So in other words, SP1 is SU2, provided you look, I mean, maybe I would be tempted to say SP1 tilde is SU2.
Yeah.
I'd really kind of rather say that SP1, what is SP1? I think SP1 is really, I mean, see, he's identified all these things, so the discussion we're having is almost impossible because he has used the same notation for all of these things,
Right.
which is fine. You know, it's not wrong or anything. It's just, you know, it is what it is. So if I have A plus I plus JC plus KD, this set of quaternions such that A squared plus B squared plus C squared plus D squared is 1. So this is SP1. I would say this is raw SP1. Raw, unadulterated SP1. And by the way, it is also our model of the 3 sphere. Viewing quaternions as 4 space. So SU2 is SP1 is S3. Okay. Fun facts. Of course, then you ask, okay, well, that's lovely. What is SP2?
Yeah.
You don't want to know?
Well, I don't quite see how we got to that definition, the raw definition of SP1 that you gave from the original of preserving the dot product.
Well, yeah, I mean, honestly, I need to recover what is the dot product in terms of tildes, right?
Yeah.
But that's just product, really. I think, I mean, here the dot product is, well, it's not the dot, it's not just product here, right? It's the one times the conjugate of the other, right?
Mm-hmm.
So,
Which should...
so it should be something like, you know, P something like r tilde p tilde, right, times r tilde q tilde conjugate is equal to, but this should be the quaternion conjugate, you know?
But we're looking at the complex 2x2 version of that.
Yeah, so my question is, how does the quaternionic conjugate translate into the world of the 2x2 complex representation of the quaternions? What is, remember? What is the quaternionic conjugate at the level of the 2x2 complex notation? That was discussed. As I recall.
So if that's
determinant of the matrix.
Hmm?
Wait, okay. Can you repeat the question? I missed something.
I think you just apply whatever the complex conjugate was to that particular representation. No?
No. Page 10. The quaternionic conjugate is not the result of taking the complex conjugate of each entry in the matrix Q. In fact, the quaternionic conjugate is the result of taking the complex conjugate in each entry of the transposed matrix. So to be fair,
So
this has to be conjugate transpose, and same over here. If I'm using bar to be the what do I mean by bar? If here I mean by bar the component-wise conjugation of 2x2 complex matrices, then now I'm right, like that. So this is, you know, r tilde, p tilde, q tilde, bar transpose, r bar, r tilde bar trans, man, goodness gracious, what awful this is. And then, yeah, okay. Q tilde bar transpose.
we can do them at the same time like that? The reverse and the bar and the transpose?
Well, the bar is innocuous. Like the product of, if I have AB, 2x2 complex matrices that conjugate, component-wise conjugate, it plays nicely. It's just this. There's nothing funny about it.
Really?
But transposition, on the other hand,
So we don't have to
tranposition does sock
reverse.
shoes.
We don't have to reverse the order on the conjugate.
no, not for
Oh, you-
point-wise conjugation. No, make component-wise conjugation.
Did you do it over there? I think you did it in your first attempt.
I did, but that's because over here I meant quaternionic conjugate,
So you
which
have to
does
reverse
have
it.
a sock shoes principle. But again, here this was a quaternionic notation, and I actually stand by this. This calculation's still legit because that's what I just got to.
Okay, so this one says this complex
We really
conjugate.
need another notation for quaternionic conjugate, which doesn't beg the confusion of the complex conjugate for complex representations of the quaternions. Sorry.
Start by making our own.
Start by making our own.
Just make it star.
Just make it star. Oh, that'll fix all our problems.
Or we can make it subscript 7.
Look here though. So all then you do is, okay, so like 1. 1 is not the loneliest number, 1 is a useful number. You just stick it in here. Set 1 equal to P, 1 equal to Q, and this gives us what? So there you go.
Yeah.
Which of course implies that this. But all right. I digress. All right, let's try to move on here. Yeah, the 2x2 symplectic matrices are uglier. They're well, like, so for H, basically you just, so like H, so for something that's like going from H2 to H2, and is an isometry of this, you would have a matrix that looks something like, you know, 4 quaternions. But what you do is you put one of these things. Basically, you put one of these in each thing, so you get this 4x4 block of
Complex.
complex, and each one of those being one of these quaternionic blocks.
Right.
And then you translate, it's almost the same calculation, but with block matrix multiplication. And it's the details are, I think they're kind of buried in the exercises, honestly. So we should try to work the exercises on page 59 to understand what it means. What does SP2 really look like? I'm going to move on here.
Are we going to get to SPN?
I think if we understand SP2, you'll understand SP3 and so forth. Probably. It's blocks.
Right.
It's just blocks upon blocks. And
Does it still look good? I bumped it.
I'll try to say something more explicit some other day, but let's go on here for now. Otherwise, we'll just be talking about these funny matrices, and it won't be that interesting. I still have hope. Okay, so maximal tori. What is the maximal torus? He says, the main key to understanding the structure of a Lie group is its maximal torus. A, parentheses, not generally unique, maximal subgroup which is isomorphic to the k-fold Cartesian product of the unit circle. So, maximal torus it looks something like the k-torus, right? It's S1. I can't make my S's with their proper superness. Well, someday I'll learn. Anyway, so k-fold copies of these, right? And so, like to start with, he claims that if you look at SO3, all right, the maximal torus in SO3 is something like, he calls it T1. It's basically things, it's like, here's a copy of it anyway. Cosine theta, sine theta, or minus sine theta, cosine theta, 0, 0, 0, 0, 1. So matrices of this form give you an S1 inside SO3. So it's like, these rotate E1 and E2 angle theta about, yeah, they fix E3, exactly.
That's what torus is.
Well, a torus is a subgroup which is isomorphic as a group to a Cartesian product of the circle, and this is, of course, the product. I mean, this would be like the direct product of the circle, the S1 groups. And he calls this one I'm looking at right here, just to keep with his notation, this is R. Oops. Doing the real numbers, what's wrong with me? He calls this R theta prime. This is his notation, R theta prime. Just to give it a name, I think. All right, so now this maximal torus, let me just run through it again. It's the I guess that's essentially the definition right here. An observation you can make about that is what? This is a what kind of group? Yeah, it's an abelian group because it's the direct product of abelian groups, which is once more abelian. All right. Now, this word maximal, what does it mean?
I mean, it doesn't have any proper subgroups.
Right.
I don't know.
I guess it means that if there's another torus, right, then let's see how to say this.
Maybe
He said, mhm.
keeps the least amount of things fixed. I mean, well, that's weird.
He says, he looks at it, he says, so let, see if we can understand from his argument here, let T be any torus which contains T1. Now, if T1, if this wasn't actually the maximal torus in here, if there was actually like an S1 cross S1, if it was actually like a T2 defined, then if we did this argument correctly, we would find out that T could be strict, it could be bigger, it could actually be like a 2 torus that contains this 1 torus.
Mm-hmm.
There's not room in SO3 for that to happen though. As we'll see shortly, he gives us an argument that it's in fact maximal. Alright, so he's like, if A is an element of T, then what can we say if A is an element of T? So it's a torus, right?
Mm-hmm.
So it's abelian. We're saying that this is a subset of T, right? Possibly you could.
So it'll commute with T1.
Right, it must commute with everything in T1. In particular, A must commute with this guy for arbitrary theta. Right? Does that make sense?
Mm-hmm.
Now he says what we're going to argue is that given this condition, we can show that A is in fact an element of T1. And he says, these details haven't been shown yet, but after we do some thinking, a little bit more thinking, all right? A is in fact an element of T1, so therefore T is equal to T1. Which shows you in fact that the torus, which is already given, is a maximal torus. It seems to me, logically, you might ask the question, how do you know that there's not some other, like, torus out there, right, which doesn't connect to, which is disconnected from this T1, right, and it's bigger? Why can't there be another torus which doesn't contain T1 that could be bigger? Why is it T1 has to be contained in the other torus we're looking at? What's in T1?
S1?
Right, what's in S1?
The center of S.
It's just unit circle.
Yeah, I think the identity element has to be in here, right?
Right.
So,
When
you know,
beta 0.
if this is inside some larger matrix group, and we're looking at, this is a subgroup after all of the matrix group, it has to have the identity, right? So, at least that much has to be. I don't know, I'm not, oh, anyway. There's something bothering me there, but there's probably a good reason for it not bothering me. Alright, so how do we prove that A is an element of T1? I mean, we're going to use this condition somehow, right? So he says, let's look in particular at, let's see here. He says, it suffices to show that AE1 and AE2 is an element of the E1, E2 plane, because in that case, that would make A an isometry of the E1, E2 plane, which fixes O, and it follows then that it has to be something in T1. So we basically want to show that A fixes E1, E2 plane. You might worry it could still be a reflection, but there's an argument to undo that too. Again, we're using E1, E2, E3 for the standard basis for R3. So almost all of these arguments, as you read on through the chapter, they're based on looking at pi or minus pi. So like if you look at R pi, which is what? R pi prime is
zeros.
And so let's see here. If we look at, so then we can look at like A, R pi prime, E1, which is what? That's going to be A times minus E1, right?
Right.
Let's see, I think he has introduced some notation. So that's minus A E1. Now what he does is he says A E1 is equal to like little a1 E1 plus little a2 E2 plus little a3 E3. So to show that A fixes the E1 E2 plane, one of our goals is to show that this is 0, right? We want to show that's 0. And likewise, if we let like AE2 equal to B1 E1 plus B2 E2 plus B3 E3, our goal is then to show that this is also equal to 0, right? If you can show those two things, then you've got at least that A fixes the E1 E2 plane. But you know what? A is also in SO3, so it's not just any old thing. It's already a rotation. It's already a rotation. Why are you worrying about it not being a rotation? Oh, something else. I don't know. I'll shut up. There's something. Sorry, the voices in my head. All right. Try to ignore them. So this gives us what? Minus A1 E1 minus A2 E2 minus A3 E3. But this is equal to what? This is equal to R pi prime AE1, right?
It's
Which
5
is
o'clock p.m.
Oh man, quiet. We aren't even to the fun part yet. Why did we just meet once a week? We should meet twice a week. Oh well, it's too late. Of course, that puts minuses what?
First, yeah.
And just leaves the third one alone. So you look at this and you look at that. They're equal. Cancel, 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 cancel. But these two together tell us that A3 is equal to 0. And basically the same argument, just erase this and put E2. E2 will give you, I mean, almost the same argument with the A's replaced with B's. We'll force B3 to be 0 for almost the same reason. Hello? I will be done in 5 minutes. Oh, what's that? Yeah, it's open. I'll come down in 5 minutes, okay? Okay, bye. It looks like you guys got out early today.
You mean on time?
What's that?
You mean on time?
Yeah, on time. Well, we started 5 minutes late. It's all your fault. I was actually here on time for once. But, yes, fine on time. Sorry for teaching you. I learned that from my wife. Let's see here. No. So that's almost what we need. That shows that A is, basically it already has shown that A is, I think that actually, because we already know that A is a, goodness, where's A coming from? Well, A is in T, but T is a subset of SO3 unless I'm misreading something here. So we already know it's a rotation. It's a rotation which fixes E1 and E2, so it's got to be one of these guys.
So what we just proved is that T1 is the maximal torus of SO3? Is that what
Right.
you just proved?
Yeah.
Okay.
So the next thing he looks at is the so-called center. So what's the center? The center of a group, right? It's the set of all things. It's A in group such that what? AB is equal to BA for all B in the group, right? And the next thing he does is to argue that the center has to just be what for SO3?
It just says the identity rotation.
Let's see here. Let me read the sentence. Listen carefully to the sentence. We'll slip past you. An element in the center of SO3, right? Commutes with all elements of SO3.
Mm-hmm.
And in particular, with all the elements of the maximal torus. All right. So the argument above shows that A. So we're talking about A in the center. The argument above shows that A fixes basis factor E3. Interchanging basis vectors, we also can see that A fixes E1 and E2. Hence A is identity rotation. That is, the center of SO3 is just the identity. Anyway, so next time we'll take a good long look at maximal tori and centers, these groups, and hopefully we'll actually finish chapter 3 next time. Oh, I'm sorry, you guys. I somehow have got to find a way to speed these up. I'm sorry. I guess I should stop delivering New Year cake in the middle of class. I'm sorry about that. Anyway, if you will do those homework problems I mentioned, which was what? Understand the
It was the sublected group stuff,
sublected
right?
group. That should be helpful to make
That
more sense of it next
was
time.
3, 4, 1 through 6, I guess.
Yeah. And then what I really want to get to is, of course, these other ideas about, interesting chapter, interesting message about simplicity and so forth, and path connectedness, very interesting, but I want to get to the exponential. My heart is at the exponentials, and that's several chapters away. We still need to talk about tangent space and such. So, but that's not hard. Let's see.
Bringing it back.
Anyway, thanks guys.